All right, very good. Welcome back, everyone. So our second speaker of the day is Camila Sehnem, who's joining us from the University of Wellington. And Camila will speak about equilibrium on Toeplitz extensions of higher dimensional non-commutative tori. Thanks for coming, Camila. Go ahead.
Thank you. Thanks for the invitation to speak. So I'll talk about equilibrium on Toeplitz extensions of higher dimensional non-commutative tori. And this is a joint work with Dara, Afsar, Marcelo, Laca, and Jack Ramagge. So quite local work. And so first is I will start reminding what a non-commutative torus is, how higher dimensional. And if we know here T is the unity circle, and we know that the continuous functions on the any torus is just isomorphic to the universal sister algebra generated by any commuting unitaries. And this in turn can also be described as the group sister algebra of Z to the N. So, but in this case, we just have commutative sister algebra, the unitaries just commute. And when we add some relations, cocycle, instead of taking a group sister algebra, we take twisted group sister algebra, and we call this non-commutative torus or higher order. For example, if we have an antisymmetric real matrix of order n, and then the n-dimensional non-commutative torus A theta is just the universal sister algebra generated by any unitaries, satisfying these relations that are encoded in the matrix. For example, when n equals to 2, then the matrix is just determined by a real number, and so this is just what we know as the rotation algebras. And when theta, when the number is irrational, then we have the well-known irrational rotation algebras, and we always studied. So, and this, then we say that these are higher dimensional because then we have more. Whenever we have an antisymmetric matrix, we have a cocycle on Z to the N squared, like a circle-valued cocycle, which is a function given by this exponential, and it is bilinear and satisfies a certain relation with respect to the conjugate. And in fact, all circle-valued cocycle on Z to the N, they come from cocycles, they come from antisymmetric matrices in this sense, in some sense. And the sister algebra A theta can also be described as the twisted group sister algebra of associated to this cocycle. Here, twisted group sister algebra is just, in the group sister algebra, we take a unitary representation. And here we don't have a unitary representation, we don't have a homomorphism of Z to the N. But if you consider but we have a representation that is multiplicative up to some scalars, and these scalars come from this cocycle. So we have a homomorphism when you consider the quotient of the unitary group by the circle. So these are higher dimensional non-commutative tori. And although in our work we can look at non-commutative solenoids, Toeplitz non-commutative solenoids, but our paper built on previous work and their motivation, and they work on non-commutative solenoids, and the main motivation come from non-commutative solenoids. So I will talk a little bit about this now. Solenoids, they are inverse limits of tori, and so the continuous algebra of continuous functions on a solenoid, they are direct limits of continuous functions on the circle. Then Latemorier and Packer, they wanted they want to define a notion of non-commutative solenoid, And they use, for this, they use a twisted group algebras. They consider the group of n-adic integers, which is then a direct limit of the integers. And so the Pontryagin duo of this group is a solenoid. And then they consider the twisted group algebra of this group of Kn squared. Pretty much in a similar fashion as the usual non-commutative torus is defined. So we have the integers, which has the torus as its Pontryagin duo, and you consider then a twisted. We can view the A theta as a twisted group algebra of Z squared. But here the duo of Kn is then a solenoid rather than the torus. They proved that this non-commutative solenoid is a direct limit of usual, the non-commutative tori. Here dimension 2. They studied K-theory and simplicity criteria and things. And then Brownlowe, Hawkins and Sims, they wanted to study KMS states for solenoids. But usually, if you have just unitaries, the dynamics coming from the gauge action doesn't have an interesting KMS state structure. But then what they did, instead of taking two unitaries, considering limits of non-commutative tori, they replaced each unitary on one unitary non-commutative torus by an isometry, kept the other unitary, and then there was the usual relation between this isometry and this unitary. And then they studied dynamics, considered dynamics for this sister algebra and for limits of this sister algebra. In this limit, they called a Toeplitz non-commutative tori, just because it was an extension of the non-commutative solenoid. This limit they called the Toeplitz non-commutative solenoid because it was an extension of the standard, the non-commutative solenoid by Patria and Packer. So this was for dimension 2. Then for higher dimension, the Afsar, Dara, and Astrid and Huef, and Raeburn and M things, they considered, they divide for n, right? You have n equals to k plus d, and they divide z to the n into copies as the sum, z to the k, z to the d. And they replaced one unitary representation of z to the k by an isometric representation, which was Nika covariance, which I'll explain a bit what this means. And they kept the other unitary representation of z to the d. And these isometries would commute among themselves, the unitary commute among themselves, but there were relations between unitaries and isometries, which were encoded in a matrix of order k by d matrix, real matrix. And here, Nika covariant means that whenever we have two elements of n to the k, and we multiply the range, the product of the range projections is compatible with the lattice structure of n to the k, which in this case is equivalent to saying that if you consider the canonical orthonormal basis of n to the k, and you look at isometries associated to these elements, the two elements of the orthonormal basis, this is equivalent to saying that these isometries star commute. So they commute, and when you commute if they are adjoint with the other as well, So this is equivalent to Nika covariance in this case. So then the higher rank Toeplitz non-commutative torus was then this is generated by one isometric representation of n to the k and one unitary representation of z to the d. They mix isometries and unitaries. And then they studied KMS states for the dynamics on the sister algebra. So for each vector in Rk with positive coordinates, this gives a dynamics on this sister algebra B theta, which is given, it fixes the unitaries, and on the isometries, it's given by this exponential, where here, this denotes we have just the scalar product between P and R. We just view P as a vector as well in RK, and then we consider the usual scalar product. And they studied the KMS structure for these dynamics. They proved for positive inverse temperatures, the KMS beta states for the dynamics were parametrized by probability measures on the D torus. And just because the sister algebra then generated by the unitary representation of Z to the D is a continuous functions on the D torus. And then the KMS beta states would come from states on the sister algebra. And they also consider limits of these sister algebras, which then they call the higher rank noncommutative solenoids. And a project started was a question of Ian Putnam. It was Zara's talk, that why we also don't want, why they wouldn't allow the unitaries instead of getting just continuous functions on the D torus, so a classical torus, we also wouldn't allow non-commutative torus as well. So why we don't add relations there as well. And then we consider then, instead of taking an usual isometric representation, we consider two-state isometric representation. So let's consider now just N by N antisymmetric real matrix. And again, this matrix gives a cocycle, a circle-value cocycle on Z to the N by the same formula we had before. And we can have a two-state isometric representation of N to the N associated to this cocycle. First, we consider the Hilbert space L2 of N to the N. And for each P, we can define an isometry on this space by this formula using the cocycle. And this gives an isometric, a two-state isometric representation, meaning that it's not a homomorphism of the N to the N, but it is up to a scalar. In this scalar is just this cocycle. And these isometries, when we multiply LP star by LQ, we have this relation. Essentially, we can move the adjoint of an isometry in the left to the right of another isometry, and we pay the price of adding this scalar. So first, when the cocycle is just trivial, all we have is that these isometries start commute when P and Q are just elements of the orthonormal basis. So this is just, it's the same as Nika covariance. When we multiply the product of two range projections is compatible with the structure of lattice structure of N to the N as well. And then we call this the any-dimensional Toeplitz noncommutative torus associated to the matrix theta, which is then a two-state semigroup sister algebra of N to the N. And in here, we are considering cocycles essentially coming from matrices, but first, again, cocycles from N to the N, they always extend to cocycles to Z to the N, and cocycles Z to the N, they always come from matrices up to cohomology. And now, how the sister algebra relates to the sister algebra defined by Afsar and Huef, Raeburn and Sims. If you consider now n equals to k plus d, and you consider our rectangular matrix k by d matrix of real entries, we can define an antisymmetric matrix just by adding here. First, we consider the square zero matrix of order k, and then we put this matrix lambda, and then here we have the square matrix of order d. So this gives a matrix of order n, which is antisymmetric. And if you consider the Toeplitz is noncommutative, the torus that we have defined, then in this case, just because we just have zero, the first on the upper corner, upper left corner, we just have zero. Then the first k isometers will commute among themselves, and the last d isometers will commute among themselves as well, because the bottom matrix is zero, the bottom right corner matrix is zero, and we would just have relations between the first isometers, and when you multiply one of the first isometers by one of the last isometers. So, and then when you make the last isometers become unitaries, what we get as a quotient is the C-algebra defined then by Afsar and Huef, Raeburn and Sims. So, and when we make everything become a unitary, then of course what we have is then the C-algebra A theta, the higher dimensional noncommutative torus. So here it's maybe more convenient to see A theta as now a twisted group algebra. Then the map which sends an isometry LP just to one canonical generating unitary is then surjective, and the quotient is just the idea generated by this complement projection. So just making all the isometers become unitaries. And this is the same thing. And as for A theta, we have also a twisted group algebra and also a presentation as a system generated by n unitaries. We can have a similar representation for this topic, this noncommutative tori, but in terms of isometers. We can also describe it as a universal system algebra generated by n isometers, satisfying these relations. So we have this commuting relation between the isometers, and we also have this relation between the adjoint of an isometry and the other isometry. This second relation, they don't need to be imposed when we have unitaries, but if you have isometers, we need to be imposed. They are not automatic, and this is the same as the Laca covariance relation that we had before. So when the cocycle, when the matrix is just zero, this is just saying that they star commute. So we also have this description, which is very useful sometimes. And now we can consider the dynamics on the system algebra, which is the same as we had before. We consider now just a vector of Rn, and we consider the dynamics, which then sends an isometry to this scalar times itself. So here again is just the scalar product of P and R. Now P is an element of n to the n, and R is a vector of R to the n. And we want to consider KMS beta states for these dynamics. Then now first recall that if a KMS beta state for this dynamic is a KMS state, which satisfies this relation, this commuting relation, whenever A is an alpha analytic element, which means that the function from R descends and T to the evaluation of the automatism of at A. So alpha at A, it extends to the entire plane and is an entire function. It extends to an entire function on the complex numbers. And And now here, so we want to study K-means beta states for these dynamics. And if we just fix an isometry and we see what the K-means condition means, this says that this number has to be smaller or equal than 1. And from this, we can conclude that all the coordinates of R must have the same sign as beta. So if beta is positive and R has one coordinate negative coordinate, then we cannot have a K-means beta state. And if beta is negative and R has a positive coordinate, then you cannot have a K-means beta state. So then that's why we consider R just, we assume that R has all coordinates of this have the same sign. And in this case, we work with positive inverse temperatures. So we assume that beta is positive and R is a vector if non-negative coordinates. And for now, I'll just omit the R from the notation of the dynamics. And if one isometry is fixed by the dynamics and we have a K-means beta state, and when we consider the GNS representation associated to the state, then the image of the isometry under the GNS representation has to be unitary. So whenever P, the inner product P is orthogonal to R, then we have that the isometry is fixed and the element you have to be unitary. And so the K-means beta state you factor through the quotient of the Toeplitz noncommutative tori by the ideal generated by these complement projections, where here each j is such that the coordinate Rj is 0. So that's why also in previous work, sorry, they could just, we can just start if unitaries from the beginning, just because you know that the K-means states you factor through the quotient. And so without loss of generality, we just assume that our vector has the form Rk and Z, that all the first K coordinates are positive and the last D coordinates are 0. So that you fix the last D isometries and the first K, you will do something, you move the first K isometries. Okay. There's a canonical gauge action of the end circle on the Toeplitz noncommutative torus, and in fact the dynamics comes from a subgroup of this action, and which is just given by this formula, where here z to the p is just each coordinate of the element z. We just take the power zi to pi, where pi is a coordinate of the vector p. And by averaging over the circle, we get a faithful conditional expectation onto the system algebra generated by the range projections. And if you restrict, we can restrict as well this action to the first K copies, to the copy of the K torus, given where we take the copy as just the first K coordinates, the projection on that. And we again get another conditional expectation. And here, then, which is quite useful, we can write we have this spanning set for the Toeplitz noncommutative tori, which is just using the relations. So we can write as LP and then something where here P is something orthogonal to the N to the 0K N to the D. So it's just an element N K and Z 0G. and X and Y are elements of ND, or the last, which is just the last D coordinates are non-zero. So, and it's convenient to consider this spanning set. And when you consider the gauge reaction restricted to this copy of the K torus, then the fixed point algebra is just the element such that P is equal to Q. So it's just the system algebra generated by these elements. And this is useful to study the KMS state of the system algebra. And in fact, here again, first K coordinates of R are positive and the last are just 0. And if you have a positive real number and we have a KMS beta state, then first, when we restrict phi to the system algebra generated by this isometries Lx, if X orthogonal to the NK copy, NK 0D, then this is a trace, just because the dynamics fixes this element. So the KMS condition will imply that the KMS state has to be a trace there. And it also satisfies this relation, which here, this implies that in particular, it will factor through the conditional expectation EK that we have from the restriction of the gauge reaction to the first, the K2 torus. And so, in particular, this means that the KMS state is determined by its restriction to this system algebra generated by these isometries. But of course, this says that it's determined by its restriction, but doesn't say whether we have KMS states and how, in which traces of this system algebra come from KMS beta states. So that's why we still need to understand. And so, and for that, we consider this projection, this Q, which is a product of complement projections. Here, if we look, we have L2 of NN. This projection just corresponds to the projection of L2 and to the N onto the space L2 to 0K times ND. Is the projection of this one space onto this subspace given by the N to the D. And so we have that when you multiply Q by an element LP, an isometry LP, if P is orthogonal to this copy of N to the D, then this is 0. And we also have that Q commutes if elements of the system algebra generated by these isometries of elements of the copy N to the D. And so the corner is the same as this given just by these elements. And in fact, this corner is isomorphic to the system algebra generated by these isometries. For the compression is injective on these elements on the system algebra generated by the isometries Lx, x in 0K times N to the D. And this in turn is isomorphic to, again, another Toeplitz noncommutative torus, which is just, if you consider the matrix is theta, and we look at the bottom, D by D bottom left corner, this is again an antisymmetric matrix and gives a cocycle on N to the D. And if you consider the twisted semigroup system algebra there, the Toeplitz noncommutative torus there, this system algebra is isomorphic to this Toeplitz noncommutative torus. And so, as in previous work, they have that the KMS beta states would come from E states on a commutative torus, and here we have that they come from traces on a noncommutative torus, Toeplitz noncommutative torus in this case. So if you consider the noncommutative beta state, it will restrict when you multiply by a certain number, we then have a trace on the corner, given by this by the projection Q. And you always have that when you apply phi to Q, have a positive number, and the inverse is just this number, that beta, which is the sum of series of exponential series. And we have that for each tracial state of the corner, then we can obtain a K-means beta state, and we have this is a weak star homeomorphism. So every K-means beta state comes from a state, a tracial state of the corner, which is given, the map is given by this formula. And this corner in turn is isomorphic to a Toeplitz noncommutative tori of dimension D. But here, so we have this map, T beta, and from traces on the corner, and then when you apply the isomorphism from the Toeplitz noncommutative tori and try to replace the map from the C-algebra that we have generated by the isometry is Lx and x in n to the d, then we have a more explicit formula. So for each tracial state on a Toeplitz noncommutative tori, and we have a K-means beta state, associated K-means beta state, which is given by this formula. Where here we are just taking tau and we look at the isomorphism between this Toeplitz noncommutative toris and the corner and using the map we had before. So this gives this formula for the K-means beta state. And so then we had this map from the Toeplitz noncommutative tori, and we know that the traces on a Toeplitz noncommutative tori, they factor, because then the isometries, they must be unitary under the generalise representation, and they factor through the quotient. And so they are just traces on a standard classical higher dimensional noncommutative toris. And then we started studying, trying to understand how the traces on a higher dimensional noncommutative torus was obtained. And I think this is well known, but we couldn't find really a reference if the clear statement. So we just wrote everything. And it follows that these traces, they will also come from a classical torus. First, given an antisymmetric real matrix D by D matrix D, which here I'm just denoted by D, but we can think as the bottom left corner from theta that we had. And we considering a subgroup of ZD, which is our elements, degenerate elements, which essentially the elements of Z to the D such that this scalar product X and dy is in Z for all Y in Z to the D. Essentially, when you apply the cocycle, and we will just have the identity, the unit. And it follows from that the noncommutative torus is AD is simple, even if this matrix is non-degenerate, meaning that the dimension of the rank of this group is 0. And if the Toeplitz if this torus, if AD is simple, then it has a unique trace, and the same, which is just the one which projects on the unit and on the identity, and the center is trivial. The center is just the complex numbers. And in general, we can find an action of a certain compact group, which here is a product of some finite cyclic groups and a D minus M torus. We can find an action such that the fixed point algebra is precisely the center of AD. And so we can have a conditional expectation onto the center. And the center is isomorphic to a commutative torus of dimension M, where M is then here the degeneracy index of this matrix. And it follows that the traces on the noncommutative torus AD, they are parametrized by probability measures on this M torus, just because the map, every trace you factor through the center, and we have a homeomorphism from the state space of the center onto the space of tracial state of AD. And then when we combine all of this, we have traces on a Toeplitz noncommutative torus. They come from traces on a standard classical higher dimensional noncommutative torus, and these in turn come from states on the center, which in turn is isomorphic to a commutative torus of dimension M. Then what we have is then that if you write the matrix theta as in this way, and we have theta d the bottom left right corner, and we consider the degeneracy index of this corner, then we have a affine Weak-Star homeomorphism of the space of probability measures on the M torus onto the space of KMS beta states of for the dynamic is given by the vector R. Here R again is first K coordinates are positive and the last D coordinates are 0. And this is the more general statement, and you can have a more explicit formula for the how the KMS states are obtained from the probability measures, but then we use a basis for the ZT, because essentially the action of the group that we had and the isomorphism of the center, if the continuous function on a M torus, they can define explicitly using a basis of Z to the D, which when we restrict to, when we consider just the first M elements, some multiples of these elements form a basis for the group H of the generating elements. And then if you want to use that basis, we have this formula for the KMS beta states, where here lambda x minus y is just -1 or 1. And this number comes from when you look at the quotient map from the Toeplitz noncommutative torus, d-dimensional noncommutative torus onto the standard classical noncommutative torus, and you try to write the image in terms of the canonical generating elements, then because of the cocycles, it will appear a scalar. In this case, the scalar will be just 1 or either 1 or -1. So that's why we have this lambda x minus y. And here this z to the c is appears just because we write the element in terms of the basis we have. And so, for example, when theta d is just the 0 matrix, all we get is then, we don't need to do anything, all we get is that the KMS beta states are then parametrized by probability measures on a D torus. And yeah, and we didn't look at, so that's all. We didn't look at solenoids essentially because of some technical reasons, which when you have unitaries, it's easier to get limiters and homomorphism between system algebras. But when you get Toeplitz noncommutative torus, because we have isometries and we need the relations between the isometries, there are some technical issues that at the end we would be in the same case as previous were. So for now, we left that for future work. And that was all. Thank you.
Thank you, Camila.
Thank you.
So do we have any comments or questions online or in the room?
Question. Can you go back to the previous slide, please?
Yes.
Okay, so you have a homomorphism from the space M1 of Tm to the space of K in beta state. So this is a homomorphism. So the range depends on the parameter beta, but it seems the domain is not. So is this saying that the space of K in beta states is the same for every beta?
No. Oh, yes. Yes, it is. Yes, it says the same, but the map is different. But yeah, the space will be the same.
Okay, so the K states don't depend on beta.
Yes, the space does not depend. The map will depend on beta, but yes, the space does not depend.
Right.
For beta positive. Right.
There is a may I say something? The space is homeomorphic, but it's not the same. So the states are changing with beta. It's just that they have the same topological or affine structure.
Okay, so homomorphic, but you don't get any phase change. Is that? I guess that's.
Yeah, there's no phase change. That's true. Yeah.
Okay, thank you.
So, yeah, we also compute for beta equals to 0 and infinite and yeah, so some changes.
All right. Any other questions or comments? If that's not the case, then let's thank Camila one more time. And Mika can stop the recording.